All right, well, welcome back, class. Here's our second digital lecture. So we're going to pick up exactly where we left off on Wednesday, talking through the implications of extensivity, this idea that thermodynamics provides two qualitatively different kinds of variables which are so-called extensive, meaning that they change with the size of the system and in proportion to the size of the system, and so-called intensive variables, which don't change as I change the scale of the system. So these are familiar functions, things like the energy. The energy is a natural function of the entropy, volume, and number of particles. All three of those functions are themselves extensive. So if I make a system that has twice the entropy, twice the volume, and twice the number of particles, well, that's the same thing as if I had two copies of a system whose energy is given by a single copy of the entropy, volume, and number of particles. So scaling the system in this case means increasing its size as codified in its volume, its number of particles, and its entropy. If I do that, then I would have the equivalent of 2 times the system that I would have had in single copies of the entropy, volume, number of particles. So we talked through also that this is kind of odd because the energy should change if I bring 2 physical copies of a system together. And so this is only a reasonable approximation when we are dealing with macroscopic systems whose surface to volume ratios are very, very small. So energy is not the only extensive function. Other auxiliary functions like the enthalpy, for example, are extensive. The enthalpy depends naturally on the entropy, the pressure, and the number of particles. And if I double the system by having twice as many particles and twice the entropy, keeping the pressure fixed, that will be like if I had 2 copies of the enthalpy at fixed entropy, pressure, and number of particles. This is pretty general. We can even talk about things like the volume of the system. It might depend, for example, on the temperature and pressure, and for a multi-component system might depend on how much of one molecule I have, call it N1, and how much of another molecule I have, call it N2. If I double both the extensive variables, both N1 and N2, holding temperature and pressure fixed, well, that's like what I would have if I had 2 copies of a volume with a single set of N1 and N2, keeping the pressure and temperature fixed. Now, this extensivity of things like the energy and the enthalpy and the volume, it has a nice mathematical structure to it. In fact, Euler taught us about that. Extensive functions are also known as homogeneous functions if they're extensive in our typical way and that they scale linearly with the system size. That means that they're homogeneous functions of order 1. And last time we went over a statement that Euler proved. He had a theorem for homogeneous functions. Which went like this: if some function f is homogeneous in both of its arguments, x and y, such that if I scale x and y by some factor lambda, I get lambda times the function f of xy. So if that's true, if f is first order homogeneous in its arguments x and y, then Euler taught us that we can in general write f of x and y in a simple way, namely how f changes with x at constant y times x, plus how f changes with y at constant x times y. Okay? So what we're going to do today is first remind ourselves of the consequences of this mathematical structure, kind of rehash a little bit of what we did last lecture, and that will essentially wrap up all we need to say mathematically about thermodynamics. So we'll start thinking about where we can take this structure, what we can learn that's of relevance to chemistry and applying thermodynamics. Okay, but first let's remind ourselves where we've been. So the fact that Euler proved this theorem, which some of you might wonder about, it's not so hard to prove. So if I wanted to, for example, if F was indeed first order homogeneous in X and Y, such that this was true, some of you enterprising students might have looked up the proof on Wikipedia. Here I'll recapitulate essentially what you'd find there. If that is true, I can prove the then statement by saying, well, if I took a derivative of f of lambda x, lambda y, with respect to lambda, well, by the chain rule, that's how f changes with x, and how lambda x changes with lambda, plus how f changes with y, times how lambda y changes with y. So this derivative is easy to do, that's just x. This derivative is easy to do, that's just y. Indeed, I have df dx. If we were being careful, we would have held that at fixed y times x, plus df dy, again being careful, holding that at fixed x times y. And over on the left-hand side, if this was true, I could substitute it in. So now d lambda f of x and y d lambda must be equal to the right-hand side. And this is a simple derivative to take. That's just f of x and y. So what we've then just proved is indeed that f of x and y, provided as first order homogeneous in x and y, can be written in this partial derivative times its arguments form. Okay, again, that's math. Why we care is that things like the energy are first order homogeneous in its variables. So the energy, being a natural function of entropy, volume, and number of particles, that it's homogeneous in each of those variables means that I can write the energy as how the energy changes with entropy at fixed volume, number of particles times entropy, plus how it changes with volume at fixed entropy, number of particles times the volume, plus how it changes with particle number times particle number if I was to fix that derivative at constant entropy and volume. That's straight from Euler, but what's cool is that we know what these derivatives mean. This is our definition of the temperature, how the energy changes with entropy. How the energy changes with volume is what we mean by minus the pressure, and analogously, how the energy changes with particle number is what we mean by the chemical potential. So what we've just demonstrated is that the energy, note not the differential in the energy, but the total integrated energy can be written as T times S minus P times V plus mu dN. That relationship let us then take a total differential with respect to that energy, and comparing that to the first law allowed us to arrive at something known as the Gibbs-Duhem equation. Gibbs, you all have heard about before. Duhem, lost to history, who knows who he was. But it's a really useful equation because it relates changes in the potentials, things like the temperature, the pressure, and the chemical potential to one another. So this is different from the sorts of auxiliary function differential changes we've seen before, in that everything under the that goes along with the d is a potential. It's an intensive function. So this lets us talk about how changes in intensive functions relate to each other. That lets us write out, for example, relationships between changes in, say, the temperature and the chemical potential. For example, if I wanted to know how the temperature changed with pressure, say at fixed chemical potential, well, I'd use this Gibbs-Duhem equation. So if I fix the chemical potential, so I'll have S dt minus P dV, now V dP, excuse me, plus N d mu, all that has to equal 0. So if I fix the chemical potential, that goes away. I can move V dP over to the other side. I'll have S dt must equal V dP. Or rearranging, I'll get dt dP, constant chemical potential, is equal to the volume over the entropy. Again, we've just related how the temperature and pressure change with respect to each other at fixed chemical potential is some entropy density, some entropy over a volume. So that's the sorts of thing that the Gibbs-Duhem provides us with. Another consequence of extensivity is that it lets us construct so-called partial molar quantities. Which are useful objects for mixtures, systems with multi-components. For example, we reminded ourselves a second ago that the volume is an extensive function. If I was to note the volume depends on temperature, pressure, and say how much of two components I have. Well, the fact that it's extensive in first order homogeneous in N1 and N2 means that I can write the total volume as how the volume changes with N1 at fixed Tp and N2, Tp, times N1 plus how the volume changes with N2 at fixed temperature, pressure, and N1 times N2. This is the total volume of the system as these partial derivatives times the numbers of N1 and N2 that I have. And we define these derivatives with a little v bar subscript 1. This is the partial molar volume, how the volume changes with N1. So what this actually means is that I can write now the total volume of the system in terms of these partial molar quantities as such. And so it must be that what this is telling us is that V bar, the partial molar volume, is how much the volume would change if a tiny amount of N1 is added. i.e. from the differential relationship, that's like saying that V, which depends on temperature and pressure, so V bar 1, if I add 1 molecule of N1, that's the smallest amount that I could add. If I ask for the difference in the volume when I add that single molecule, that's the partial molar volume. This is in principle divided by some dN1, but that's just N1 plus 1 minus N1, which is just 1. So it really is the change in the volume divided by 1, so it's really just a change in the volume as I add 1 molecule to the system. And we started thinking about whether or not this was related to, for example, the excluded volume of a molecule. That seemed, naively, that kind of makes sense, that the change in the volume might be related to how much physical space a molecule takes up. But this is actually rarely the case. We can demonstrate that mathematically for an ideal gas. And doing this for a mixture. So the ideal gas, defined through its equation of state, that PV is equal to nRT, or how the cool kids write it, kBT times N, and N we'll write as a sum of Ni's, because we have a mixture of some number of components, where it must be that if I sum over all of the Ni's, I get N. So the partial molar volume of species 1 is how V changes with adding some amount of species 1 at fixed T and P, and all Nj not equaling 1. Rearranging the ideal gas, that's just kBT over P. From the ideal gas, kBT over P is just what I mean by V over total N. So the partial molar volume of particle number 1 is just the inverse density of the system, which is much, much greater than some molecular size. So how the volume changes in a gas as I add 1 particle has nothing to do with the particle size. It just has to do with the fact that the volume is intimately related to, the thermal pressure of the system as codified in this ideal gas equation of state. That's some math. We can actually explore this just with some pictures too, for example, with liquid water. So liquid water, it has an oxygen and 2 hydrogens, which can hydrogen bond. Forming hydrogen bonding patterns that might look, for example, like this. Which of course are extended in 3-dimensional space. But just by drawing a typical hydrogen bonding pattern like this, water 4-fold coordinated, most of them have 4 hydrogen bonds on average, it's quite clear that in the course of natural fluctuations of the water, the fact that they hydrogen bond in this way means that it's quite likely that there are cavities that form, little voids, for example, here. So that's a natural cavity, a region where there is no water density. that would spontaneously form. One could imagine that I could fit in that cavity a little solute. Like take, for example, H2. That's pretty small. It probably could fit in there. Again, fit in this little cavity. If it could fit in there, it would do so without disrupting how the water are arranged. If there's a little hole in the liquid that a solute could occupy, if I put that solute in, would the volume change? No, the volume wouldn't change. Water just hydrogen bonds around it. So that would mean that the partial molar volume associated with adding H2 to liquid water would be really close to 0. Now, imagine instead of putting something pretty inert like hydrogen gas in that little cavity, we stuck an ion. Now, an ion, be it positively or negatively charged, is going to interact very strongly with the surrounding water. So imagine we put in, for example, a fluoride ion, something with a negative charge. It's going to grab on and hold tightly to the hydrogens on water. So how would water reorganize through those interactions with the fluoride ion? Well, it would get a lot closer. It'd start to fill that cavity that was open spontaneously. So then how does the volume change? So that makes it sound like the volume actually decreases. The water gets closer together. So that consequently would mean that for a little ion that could fit spontaneously in that cavity, the partial molar volume, how the volume changes as I add that ion in, might be negative. Indeed, for something like magnesium sulfate, it is actually negative. Magnesium is small enough to fit in those little cavities. It actually pulls water molecules closer together. Okay, so these quantities exist, have been measured, are put into tables. You could go look them up. They work for not only the volume, but also work equally well for other extensive functions, like, for example, the enthalpy and entropy. For the enthalpy, I could define the enthalpy as some partial molar enthalpy of species 1 times some amount of species 1 plus some partial molar enthalpy of species 2 times the amount of species 2, where this is defined analogously to the way partial molar volumes are defined. So it sounds like this makes life easy. If I have some mixture and I wanted to know the enthalpy or the entropy or the volume, I just go up and look. I just look up these partial molar quantities for the 2 different species, add them together in this simple way, and I'll know what the enthalpy of the system is. And while that's true, there is a catch. Which is that all of these quantities, partial molar volumes, enthalpies, etc., all depend on the other thermodynamic variables like the temperature, the pressure, and the composition. So these are continuously varying functions themselves of all these other thermodynamic variables, making them in practice kind of cumbersome to use. Nevertheless, if the dependence on, say, the temperature and pressure or the composition is weak, well then over a range of those parameters, you can imagine actually employing these partial molar quantities to do calculations. I think you'll have some chance to play around with that in your homework. Okay, so that's a review of kind of where we've been, some implications for partial molar quantities, elucidating more structure of thermodynamics. So now we get to something, we get to actually start applying the structure of thermodynamics to some more interesting, more chemically relevant applications. And so we're going to, over the next couple weeks, consider a number of different applications which all have the same theme, which is that they all are questions associated with so-called mass equilibrium, which is concerned with the question, how do molecules distribute themselves? In space or in solutions or between different phases or even compositions or compounds. So concretely, a couple examples. Questions in mass equilibrium might be concerned with, for example, a setup all you organic synthetic chemists are very familiar with. Imagine I take a separatory flask. I think that's what this object looks like. I don't have too much experience with it. I'm told this is a useful thing to store different solutions in. So imagine I have one solution, the blue solution lives down here. Another solution, the yellow solution, lives up here. And there are solutes in that solution which partition themselves differently between the two different liquids. So a question of mass equilibrium would be where the solutes are in different solutions. Okay, that's a question of mass equilibrium, where if, for example, I start with most of the solutes in one solution, is the direction of spontaneous change for that concentration when I put it in contact with the other solution. It's a very physical thing what one could imagine asking. Similar to that, I could ask not about multi-components, but about a single component. Imagine I go back to my canonical glass of water, filled to some level, but you know, I like to, it's getting hot, put a little ice cube in that water. So if I fill that glass up, there's some water, liquid water, down at the bottom of that glass. Let's get fancy. I could try to shade this. Oh no, that didn't work. Oh. Okay, let's leave the ice that color. So there's liquid water in contact with a piece of ice that is also in contact with its vapor above it. A question of mass equilibrium I might ask is, where do the H2O molecules distribute themselves? More specifically, which phase do they distribute themselves in? This picture has 3 different phases in contact with each other. The water could decide to stay in the liquid, could evaporate and go to the vapor, or alternatively could condense onto that piece of ice, increasing the size of the solid. It's another very physical question in mass equilibrium. What phase does an H2O molecule adopt? Slightly more abstract, one could imagine a single molecule, say something like cyclohexane, my best example of a chair. It can, in principle, change its conformation, go to a boat. A question of mass equilibrium might be, which conformation does cyclohexane adopt? And because I can, cyclohexane, if it's been spoiled a little bit, might be something like this color. Okay. Similarly abstract, I could imagine grouping states in terms of whether H atoms are monatomic, move around as H atom, or bond to form a molecule of H2. A question of mass equilibrium might be then how H atoms distribute themselves in this different compound. Let's see, what should hydrogen be? Red. It usually is caught on fire, right? All right, so these are all questions of mass equilibrium. They're all questions of where mass spontaneously evolves to. If I put an ice cube of water out here on my desk table, well, the table is at ambient conditions, ambient temperatures. I know from experience that the ice cube is likely to melt. So there's a direction of spontaneous change for the water molecules from their solid state that convert them spontaneously into their liquid state. It's a question of thermodynamics, question we're now equipped to ask. And in fact, all of these questions are answered by the same sort of tool. It's a tool we've already introduced, namely the chemical potential. Provides a compact way to address all of these questions. We already know, we've demonstrated a few classes ago, that if, for example, one group of states, call it C, had a chemical potential, call it mu C, and another state had a chemical potential, call it state B, with chemical potential mu B, that if mu C was greater than mu B, chemical potentials for the C state larger than the chemical potential for the B state, molecules will spontaneously move from which direction? From C to B. Direction of spontaneous change is from high chemical potential to low chemical potential. And they'll keep doing that until they reach equilibrium. Or, for example, C is all gone. Okay. So again, over the next few weeks, we're going to consider both the thermodynamics of these sorts of processes, why one state might be more stable and under what conditions would it be, as well as the statistical mechanics. What are the molecular features that endow those states with different stabilities? We're going to start with these sorts of instances of phase equilibrium, and begin a discussion of phase transitions. So phase transitions are pretty spectacular things that happen out in nature. They're abrupt changes to the material properties of some system. And many examples of phase transitions you all have common experience with. Some, or probably many, you don't have common experience with, but you might have heard of. Let's consider two that you do have common experience with. The first is the transition that takes liquid to its vapor, we call that boiling, or its reverse, taking a vapor to its liquid, we call condensation. So of course you have common experience with this every time you cook, likely every time you make a cup of tea. It's a process which would help sanitize some of your clothes and your food. So in such a phase transition, like many phase transitions, these are nicely summarized by objects known as phase diagrams. So let's plot a phase diagram for boiling in, say, the pressure volume per particle plane. Okay, so if I start at very high volume per particle, well, that's very low density. That's a vapor or a gas. If I was to decrease that volume, make the volume smaller and smaller, the pressure has to go up. That's from stability. If I did this at some fixed temperature. And what I know from common experience is that as I change that volume, there will be a point at which the vapor abruptly changes to a material which looks qualitatively different. And indeed, the pressure increases much faster as I continue to decrease the volume. That abrupt change, an example of condensation, takes that vapor at high density, at high volume or low density, to another state of matter that exists at high density, and that's what we mean by a liquid. Now, if I did that same sort of experiment at a different temperature, I get a similar sort of result. There would be a point of which I'd spontaneously change from a vapor to a liquid, and the liquid becomes much less compressible, meaning the slope of this pressure-volume relationship is steeper. This might be at some T2 greater than T1. Now, there is a temperature over which I do this experiment, and I no longer see an abrupt change. I might have an inflection, but the vapor doesn't abruptly transition to a liquid. If I marked out the locus of these points, I'd get a little curve. This ends at some special point. There's a maximum to this curve. If I were able to prepare a system underneath this curve, what I would see is some amount of liquid spatially separated from some amount of vapor. Those two phases then are in coexistence. And indeed, all points under this curve would act similarly. Now this point, this maximum point beyond which the vapor is distinguishable from the liquid, has a special name. We call this a critical point. It's a point in which I stop seeing these abrupt, singular changes in the property of my material. Now, if I was to think about liquids and vapors, what is really distinguishing about them? Well, this plot gives us some insight as to what we mean. What we mean by a liquid in comparison to a vapor is that a liquid is much more dense. Both are fluids, both fill the shapes of their containers, but a liquid just is a much more dense arrangement of atoms and molecules. That's the fundamental difference between these two phases. Such a parameter that distinguishes two phases we call an order parameter. It's the aspect, it's the parameter that distinguishes two phases. And for the liquid vapor transition, the order parameter is the density. Another transition we have common experience with is what happens if you take that piece of ice and leave it out on your counter. It will melt. Alternatively, you created that piece of ice from liquid water, presumably by freezing it. Now, those two, a liquid and a crystal, they also have different densities. If I was going to draw a phase diagram, maybe I'd do this one in the temperature density plane. Well, the way I take a liquid and turn it into a crystal is by cooling it down. There will be a point at which, as I cool the system down, I change abruptly from a liquid to a crystal. I could do this then at different pressures, maybe this pressure here. See another abrupt change. Maybe a different pressure up here. See another abrupt change. I could trace out this locus of points too. So I have a liquid over on the left at lower density than the crystal over on the right. In between, at densities in between that of the crystal and the liquid, if I prepared the system, I would find it at coexistence. if I set the system density to be something which is intermediate to what the system would like to be in a liquid or like to have for its crystal, well, the way it would mediate that is by forming both in some proportion. And there's a region of coexistence between the region of pure phases on the far right and far left. So indeed, liquids and crystals do have different changes in density. But there's not often a big change, not like a liquid vaporizing or a gas condensing. And while a liquid always has a lower density than a vapor, the same is not true with liquids and crystals. If I take, say, methane and freeze it, its crystal will have a higher density than its liquid. But you all know that ice floats, and that's because when I freeze water, ice has a lower density than liquid water. So density doesn't act in the same way as an order parameter for liquids and crystals or for the freezing transition. It's something a little more subtle. Now again, this sort of phase diagram gives us a hint as to what that is. I typically prepare crystals from liquids by cooling them down. Now what thermodynamic property becomes less important as I cool the system down? Well, that's the entropy. If I think in terms of the Gibbs free energy of a system, that's an enthalpy change minus T times an entropy change. At zero temperature, entropy changes don't matter. I just care about what state has a lower enthalpy or energy. So as I cool the system down, the entropy becomes less important. Crystals become favored. It's not hard to imagine, in fact, it must be the case that crystals nearly always have lower entropy than liquids. And I think that should make sense. Entropy is just multiplicity, the number of ways something can happen. In most cases, crystals, periodic arrangements, have lower entropy than liquids, which are disordered. Now, you all know that entropy is not a measure of disorder. So indeed, there are counterexamples where there are crystals that have higher entropy than their liquids. So indeed, entropy, though similar to, in many cases, like an order parameter, is not also an order parameter. But something related to entropy is there's something that correlates with disorder. It is something that correlates with disorder, and therefore disorder correlates with entropy. Really, the fundamental difference between a liquid and its crystal is its symmetry, a measure of how much disorder there is. A crystal looks the same if I was looking at a molecular arrangement corresponding to a crystal. If I look in very specific directions associated with lattice planes, I see the same thing statistically. But that happens only at discrete angles or discrete translations. I look in very specific directions, I see the same thing. I have to look specifically along lattice directions. Whereas a liquid, a disordered arrangement of molecules, statistically looks the same in every direction. It's uniform. So in fact, a liquid always has a higher degree of symmetry than a crystal. And that really is the fundamental difference between liquids and crystals. That probably sounds abstract. That's a very poorly written symmetry. Symmetry, a little better. That sounds a little abstract. We'll make that quantitative with some more pictures and some math next time. All right, thanks for tuning in.